Let's talk about calculus in polar coordinates. What would dr d theta mean? Well, if we think about it, it's the rate of change of r with respect to theta. If we looked here at this particular example, as theta increases, so does r. So we'd say dr d theta is positive. But as we look at this, the slope of the tangent to the curve is definitely negative. So dr d theta is not anything to do with the slope of the tangent to the curve. It is simply the rate of change of the radius with respect to theta. Let's look at some different rates of change then on this curve, and we're going to decide if they're positive or negative or zero. So at point A, if we change theta, increase it a little bit, we see that our radius r also increases. So this rate of change would be positive. As we change theta, we see that x increases because we're moving this way. So that's also positive. We see that y also increases. That's also positive. And then dy dx is the slope of the tangent to the curve, and we see that that's also positive. Okay, let's look at point B. As we increase theta, we see that r is increasing, so that's positive. But we see that x is decreasing, so that's negative. Y is increasing, so that's positive. And the slope of our tangent to the curve there is negative. Let's look at point C. We see as we increase theta that r is actually getting smaller now, so that's negative, and so is x. And y, actually the rate of change there is 0 for our y, and also for our slope of our tangent to the curve. Okay, let's look at D. As we increase theta, we see that r is decreasing, and we see that x is also decreasing, and y is also decreasing. The slope of our tangent is positive. Now as we look at this, the slope of the tangent to the curve is dy d theta over dx d theta. You can see here we have a positive divided by a positive, which is positive. Positive divided by a negative, which is negative. 0 divided by a negative, which is 0. Negative divided by a negative, which is positive. So if we need to find dy dx, we can take dy d theta over dx d theta. Let's look at this curve, and let's look at the area that is swept out as we increase theta. So we start here at 0 and we increase theta, and you can see as we go we are generating an area inside of this polar curve. We have a 3-petal rose, and here you can see if we went to our angle being about pi over 3, we swept out the area of this leaf of the rose. We're going to be thinking then about areas. So as we do that, let's see how we could divide up this area if we're looking at this polar curve. And because everything emanates from the pole here, they're not going to be rectangles. So we would have the sector of a circle, a piece of a circle that has radius r and a little delta theta right here. So how would we find the area of a sector? If we remember from trig, let's remind ourselves. We have proportionality here between a sector in a circle and a full circle. So we can look at the angle of a sector theta, compare it to 2 pi, and that will be proportional to the area of this sector compared to the area of this whole circle, which is pi r squared. Then we could solve this for the area of the circle by multiplying by pi r squared both sides, and then we could cancel the pi's. So the area of a sector is 1/2 r squared theta. So now we can go back and have a look here, and the kth sector's area would be 1/2 the radius of this kth sector squared times delta theta, which would be this angle right here. You can see where we're going with this. We could sum up these sectors and get an approximate for the area if we had n sectors. And one of the ways we could express this radius is as a function of theta. So let's go ahead and do that, and then you know where we're going with this. The limit as n approaches infinity of these sectors, and that is the definition of this integral. So we could integrate from a to b, a being the theta right here, b being the theta here, and we'd have 1/2 f of theta squared d theta. Now what if we didn't want to go clear to the pole, but we had this piece out here? And as you look at this, you could see that if we found the area of this piece right here and we subtracted off the area with g of theta, that we would have left this yellow shaded area. So we would integrate from a to b 1/2 f of theta squared d theta, and then subtract off this piece right here. And then we could factor out the 1/2 and combine the integrals, and we could express this area between two polar curves then like this. Now let's look at arc length with polar curves. First of all, if we had this polar curve and we could take this little segment, we know that the length of this is a Pythagorean theorem, square root of the change in x squared plus the change in y squared. Well, let's take this and let's divide this by delta theta, and this is, I put it inside the parentheses, so this is squared, so we would need to compensate that by multiplying by a delta theta squared. And then we could factor this delta theta squared out and go ahead and square root it and put it outside of the square root here. Now as we look at this, we then could take the limit as n approaches infinity of these little segments, and this is what we would have. So here is a formula for the arc length when we have a polar curve. So if we want to know the length of this polar curve from theta equals alpha to theta equal beta, we could take this integral from alpha to beta of the square root of dx d theta squared plus dy d theta squared d theta. Now we could also express this just a little bit differently. If we had this, we can go ahead and figure out what dx d theta is and dy d theta is in terms of just r and theta. So if we did that, this is just simply taking the derivative here, which is a product rule, first times the derivative of the second, which is right here, plus the second, the cosine theta, times the derivative of the first, so there's our dr d theta. And similarly over here, here is dy d theta then with the product rule, first times the derivative of the second, plus the second times the derivative of the first. Now, if we multiplied all this out, we could simplify this. This one would give us an r squared sine squared theta, and the middle term would be negative 2r dr d theta sine theta cosine theta, but the middle term over here is going to be the very same thing but positive, so those middle terms are going to cancel, and then we're going to have plus dr d theta squared cosine squared theta plus, and this will have an r squared cosine squared theta from the first term here, and we canceled the middle terms, so plus dr d theta squared and sine squared theta, and all of this is still underneath the square root, and we still have the d theta, just writing this piece of it so we can see how to simplify it. And here's my favorite trig identity. We could factor the r squared out here, and we'd have sine squared plus cosine squared, which just equals 1, so those would cancel and leave us just an r squared there. Same trick here. So this simplifies down to the integral from alpha to beta of r squared plus dr d theta squared d theta, and this would give us the arc length. So we now have formulas for finding the slope of a tangent to the curve, the area of a polar curve, and also the arc length of a polar curve, and examples will follow.